Today we're going to talk about invariance. I'll present the definitions here, and I'll try to talk about it a little less formally than the book does. The definitions I've written down here formally, but I'll try to explain them a little less formally. All the proofs and the formal development you can find in the text itself. So let's start with a finite game G, which consists of X, Y, and A. X is the set of strategies for player 1. These are the pure strategies for player 1. Y is a set of pure strategies for player 2. And A is the game matrix. That's a function which tells you for a particular choice from X for player 1 and from Y for player 2. A of XY tells you the return. That's always the amount paid from player 2 to player 1. And here we'll let G be just some one-to-one transformation of Y onto itself. You can think of that as kind of a reordering of elements in Y. We say the game is invariant under G if for every X there's a unique X prime such that A of XY is A of X prime G of Y. Or if we let G bar of X be the choice of X prime for a given X, we can say A of XY is A of G bar of X and G of Y. What in the world does that mean? Well, that means this one-to-one transformation G is renaming the elements of Y. G bar of X is a corresponding renaming of the elements in X, and what this says is that the game is invariant under this transformation if after you've renamed the elements of Y and done the corresponding renaming of elements in X, the payouts are exactly the same. So we can talk about many different transformations under which a game might be invariant, and it turns out they form a group. Why is that? Well, if you have a transformation, you can talk about the inverse transformation. G is a one-to-one transformation. G inverse is then thus a one-to-one transformation of Y, and you can invert G bar as well. And if a game is invariant under G, it'll be invariant under G inverse. The identity transformation, which doesn't change anything in Y, and the corresponding identity transformation on X that doesn't change anything in X. It's clear that a game is invariant under that. And we have this product which consists of composing transformations. So if a game is invariant under two transformations, it will be invariant under the product or composition of these transformations. So we can then talk about the concept of a game being invariant under an entire group of transformations if it's invariant under each individual transformation in that group. Now, why would we care about games being invariant under a transformation? Well, remember, being invariant under transformation means when we reorder the elements in Y and we'll have a corresponding reordering of the elements in X under which the game behaves exactly the same. The payouts are exactly the same now after we've reordered the elements. Well, the idea is if the game behaves the same, then there should be strategies which treat these elements the same. And to make that more formal, we'll define what it means for a strategy, say a strategy Q for player 2, to be invariant under transformations. It means if Q is a strategy, it gives certain probabilities. We've been calling this Q sub 1 through Q sub n in the past. Now they're just calling it Q of 1 to Q of n, because what we want to do is say if we take that mixed strategy Q and rearrange the elements according to the transformation, if that gives you the same probability vectors you started with, then we say that's a strategy that's invariant. That mixed strategy, we should say, is invariant under the group G if when we do that for any transformation little g in the group G, you get the same probability vector. And the same idea for player 1. If you have a probability vector for player 1 that represents a mixed strategy, P1 through PM, then we say it's invariant under the group if when you rearrange the elements of X, the choices for player 1, that's just rearranging the numbers 1 through M so that you're just switching the order of these things, it ends up being the same probability vector. And then what does it mean that for a game to be invariant under a group of transformations? Well, here's the big theorem about invariance. It says if you have a finite game, as we've been talking about, X is the set of pure strategies for player 1, Y for player 2, and A is the matrix or function that tells you the payouts. If it's invariant under a group G, then there have to be optimal strategies that will also be invariant under G, that will treat any elements that get mapped to each other under transformations in the group G. It'll give you the same probabilities in that optimal strategy. And remember, there could be many optimal strategies for a player. What this says is there has to exist an invariant strategy. And let me say that again, an invariant optimal strategy for player 1 and an invariant optimal strategy for player 2. There might exist some optimal strategies that are not invariant, but if the game is invariant under a group G, so that renamings don't affect the play of the game, then it should make sense that there will be optimal strategies in which it won't matter for these strategies which of these things that's getting renamed is being used in any position. Here's a simple example that I'll just talk about, and I'll write down some other examples. In the rock, paper, scissors game, you all know rock beats scissors, scissors beats paper, paper beats rock. So if you just reorganize them, instead of calling it rock, paper, scissors, call it paper, scissors, rock. That transformation among the choices, say for player 1, and the exact same transformation since they're the same choices for player 2, the game is invariant under such transformation. If in the original game you had rock beating scissors, after you transformed rock to paper, paper to scissors, scissors to rock, instead of saying rock beats paper, it would be just the same as saying, instead of saying rock beats scissors, it would be just the same as saying paper beats rock. But the game would play exactly the same way. What does that mean? Since we can apply this same transformation again, starting with rock, paper, scissors, we could transform that to paper, scissors, rock, and we could then apply that same transformation a second time to get the scissors, paper, scissors, rock, paper. We just apply that transformation twice, and then we can apply it 3 times, get back to the original ordering. It tells us that all 3 choices play kind of an equivalent role in this game. So there should be an optimal strategy which is invariant under this transformation. Well, it turns out there is. The optimal strategy is 1/3, 1/3, 1/3, gives exactly the same probability to all of these 3 choices, the only choices in this case, but exactly the same probability to these 3 choices that can be transformed one to another in this, through these transformations in the group G under which the game is invariant. And I'll remind you, the proof of this theorem is in the book. I won't go through the details of the proof here. Let's talk about another very simple example, an extension of the odds-even games. The regular odds-even game you can think of as you have 2 players. Each player puts out 1 or 2 fingers. Player 1 wins if the sum is odd. Player 2 wins if the sum is even. And we'll talk about winning, meaning getting $1 from the other person. We've talked about the matrix for that game. An extension of the game would be each player picks either 1, 2, 3, or 4 fingers. And again, player 1 wins if the sum is odd. Player 2 wins if the sum is even. For example, 1 and 1, that's even, so player 2 wins $1. That's represented by the -1 here. The 2 and 1 is odd, so player 1 wins $1. And there you see all the payouts in this game. Well, I say this is really, it should be clear that this is really just like odds and evens. Why? Because the 1 and 3 play essentially an identical role in this game. There's no difference between playing a 1 and a 3. So if you think of a transformation that interchanges the 1 and the 3, that would be the G in our situation, and the corresponding G bar would interchange, say, the 1 and the 3 here. The game plays exactly the same if you interchange these. As a separate thing, there's another transformation that interchanges the 2 and the 4, and the 2 and the 4, and the game plays exactly the same if you do that. There's no difference in the gameplay with the 2 and the 4. So one thing we can do is say there must be an optimal strategy in which 1 and 3 play identical roles, and an optimal strategy in which 2 and 4 play identical roles. And you can combine these and actually see there have to be optimal strategies in which all of these play identical roles. But let's just start with the 1, 3, and the 2 and 4. When we think about that, we can kind of reduce this game just using the 1 and 3 and the 2 and 4 as separate. The transformations that interchange 1 and 3 and the transformations that interchange 2 and 4 as being separate groups of transformations under which the game is optimal, we can kind of reduce it to a 2x2 game where, say, row 1 for player 1 is picking a 1 or a 3, row 2 is picking a 2 or a 4, a 1 or a 3, and a 2 or a 4 for player 2, and the payouts are just as you'd expect, a -1 here, a 1 here, a 1 here, and a -1. And of course we can solve this very easily, and we see that the optimal strategy here is just P is 1/2, 1/2. Of course the value is 0. We've looked at this before. Q is 1/2, 1/2. Now what does it mean that in our original game there are optimal strategies that are invariant under these transformations? That means that the 1 and the 3 should get equal weight. So if we know that 1 or 3 gets probability 1/2 for player 1 in an optimal strategy, and the 2 or 4 gets probability 1/2, that means in the original game we split that 1/2 for the 1 or 3 into 1/4 for 1 and 1/4 for 3, and we can split the 1/2 here for the 2 or 4 into a 1/4 and 1/4. So that tells us very quickly that the optimal strategies are just 1/4, 1/4, 1/4, 1/4. And of course you could have figured this out using other techniques. We have equalizing strategies and all in this 4x4 game, but it's kind of a triviality to just reduce it to the 2x2 version. The value of the game, of course, is still 0. Here's a much more interesting